And hello, everybody. I'm Georgina Maldonado, and I am the product manager for the Moses software product for Bentley. I'm going to be sharing with you some mooring system modeling options with Moses. I know lately there have been a lot of questions about Moses mooring capabilities, and hopefully this will answer some of them. So here I'm going to be talking you through a sample file. This is the MP-More sample file that comes with Moses. And at first, I'm just going to quickly go through the command sequence. We just finished looking at where the mooring system definition is, and here is where you can check some of the properties of the mooring system to calculate the hydrodynamics. Here we define the environment, and then here's where we're going to do the linear analysis. We can report added mass and damping, and then report some RAOs, and then some statistics of motions and of forces. Next, we're going to go into the S-response menu, which includes some of the non-linearities. And you will notice that some of the commands look the same as they did in the strictly linear response for example, when we reported the RAOs and when we reported the statistics and the connector forces. And then at the bottom of this command file, we are going to do a time domain analysis, which is a true nonlinear analysis. It solves the equations of motion at every time step. And for this type of analysis, there is a different set of commands to report all of the results. It is all within the PRC post menu, which stands for post-processing. And we check the connector forces and some trajectories and some motions. And now I'm going to run it. And even though this is a video, this is how quickly the analysis ran on my machine. And now we are going to look at the log file. Okay, it's a good idea to always review the log file before you actually start looking at the output file. For example, the log file contains a lot of messages that Moses wants to tell us. We're seeing the results of equilibrium, for example, what environment was used when the statistics were reported, where the location for the RAOs were reported, and here is when the database is being saved during the time domain. And here are some options that we will discuss in more depth a little later as far as plotting. So here with the variables we have available for plotting. And of course, you can send some results to the log file. It's not the results are not strictly going to the output file. You do have a little bit of control over that. And then at the bottom of the log file, it's always good to finish normally. Okay, so that's really one of the things you really should check. So here are some of the graphics results. Here's the mooring system without tension, and here's the mooring system with tension. And here is the results of some of the testing that are some of the checks that we're doing on the mooring line. Okay, so now when we review the output results, so on the left-hand side, I'm going to highlight what commands created the table on the right-hand side. And I'm doing this because as an engineer, right, you, for example, will be asked to produce the RAOs. It is important to know which command you need to produce the RAOs. So you need to be able to associate the command with the output file. And for example, here's the motion response operators generated by FR_point. And then for statistics, most of the commands that report statistics start with an ST. So on the left-hand side, you can see ST_point and ST_C force for the statistic point and the statistics of the connector forces. And again, you see that for S-response, which includes some of the nonlinearities, a lot of the commands look the same as those that when we computed the strictly linear response. And then from there, we are going to go into the time domain analysis. And in the time domain analysis, we, for example, computed the connector forces. And here is the connector forces at every event. This simulation was for 300 seconds, and you will see that this table contains all of the results for each event. Okay, and we can basically make a table for this type of result for most of what is computed. And looking at the screen, you're saying like, the table, it's nice if I want to look at a specific event, but really I want to I want to have a better option for presenting these results. And that's what we will be looking at in just a moment, because you can in graphical form. Okay, so here we're finishing up with the motions of the selected points, and we're going to again go all the way to event 300. And again, presenting the results in this manner makes it difficult to digest. And next we are going to explore what some of the options are for presenting our results. So I'm going to start off by showing you what is the system that we are analyzing. So this is just a simple barge. It looks very rectangular, and we defined a spread mooring system. And I put the name of each of the elements on the picture. On the right-hand side, in the red tab, it shows you which element is being highlighted. And I also put the environment direction that we're looking at. So elements F and G are expected to take the highest load in our analysis. So as far as options go, Moses does come with some plotting capabilities, and that's what we're going to look at first. And again, we are going to do the plots because we saw that the tables, that's presenting it in that manner makes the output a little difficult to digest. So when we review the log file after the time domain analysis, here is the list of variables we have available. And for example, if we want to get the magnitude of the lines, we could add the plot command. And for the plot command, you need to first look at this a variable list, and you need to get the number next to the variable that you want to plot. So I'm going to make a plot of the tensions on the port side and then the tensions on the starboard side. And remember, when we were looking at our top view of our system, it was lines F and G that were expected to take the highest load. And that was because the environment was 90 degrees, which on our screen is from the bottom of the from the bottom of the screen to the top of the screen. So I'm putting some subtitles, and I always empty out that register. So that's why there's a subtitle with nothing after it, so that the rest of the plots don't have some weird title that is going to maybe confuse me. So now that I ran the analysis again, here is my plots. Here's the magnitude of A, B, C, and D, and you can see the maximum is about 117, and then E, F, G, and H, and you see, wow, it went all the way up to a 610, and that's what we expected. Okay, so I know that some people, they would rather use their own plotting programs, and for Moses, we also give you that ability. We're going to generate that same table, but we're going to put the data available for Excel. So here we are again on our command file, and we need to tell Moses what kind of table to make. So that's what I'm adding. It's a pdevice HTML. And after the report command, actually it just has to be within that set of commands, lines 152 to 159 were in the disposition menu. So I just told it the channel, and then I told it to store everything. And then I'm going to look at my answers directory. And in my answers directory, you see there is now a tab00001.htm. Now I'm going to open my Excel program, and then I'm just going to drag it over, and you will see at the top of the columns has those same variable names that was in that variable list. So now I can plot all of that however I wish if I wanted to use Excel. I also know that a lot of people want to also use SQL. We also have that option available, and I'm going to also add it to our commands. So after the store command, if I just put the database command, so I just added a line, I'm going to save and run the analysis again. And then I'm going to open up my SQL reader. Now for the SQL reader, I just picked whatever comes free. I know some people are picky about their SQL readers, but I just wanted to show a default. So here is the answers directory, and you see that now there's a tab 0001. And then I'm going to open up my SQL reader. And it should. Okay, here's the SQL reader, and you can see that I can just drag that over, and here again are all of those values ready for us to plot. And if that's how you want to include them in your report, then that's also available. Okay, so that was just the options for how to do some of your reports. But we also have some options for defining the mooring lines themselves. So I'm going to show you defining one segment, adding a buoy midline, and then changing the properties of the second segment. Again, this is that same command file, and now we're going to look at it a little closely. Again, this comes with the samples that come with Moses. And here are the point names where the fairleads are located. And later I'm going to show you again that top view, and we're going to be able to identify these points. Here is the class properties, which is the properties of the mooring line. For example, what's the depth of anchor, the total length, the buoyancy diameter, and the weight per length. And then lines 48 to 55 are the connector definitions themselves. Okay, and for those, it's a little easier to understand if you actually look at those on the top view. So we're going to go ahead and look at the top view. We're going to need to zoom in because when Moses opens up the viewer, it tries to include everything. So you see the mooring lines, you can see the fairlead end and the anchor end. So we're fairly far up. So we need to zoom in. And then I'm going to show you, I'm going to highlight element A, and on the right-hand side, there's going to be a tab. That red tab is going to show you that I have highlighted element A, and you can see where I defined it in the command file, and you can see I'm giving it an azimuth, negative 45 degrees, and now I'm going to move on to element B, and you can see that the tab changes when I click on the element, so we're able to identify it. And you can see also, okay, so there's element D. And now on the next one, I'm changing from the negative azimuth angles to the positive azimuth angles. So here's element E, which is positive 135. And then elements F and G. And remember, for our analysis, our environment goes from the bottom of the screen to the top. So elements F and G are expected to take the highest load. Okay, so those were the elements. And now I'm going to go ahead do that again, but now I'm going to change the tab. It's going to now be that purple tab, and I'm going to show what the fairlead node name is. So these were MLBs, and now I'm going to show that for the next two mooring lines, it's MLC. And you can see that that keeps changing in the tab over on the right-hand side. And that's why I'm trying to show it to you with the command line with the command file open so you can see where it was defined and how it is used. Okay, so now we're going to view it from the starboard side, and we're going to view it from the starboard side so that we can see that we have a nice catenary shape to our mooring system. Again, we need to zoom in, and okay, so this looks fairly nice. Again, I'm using a very simple setup here because, as you saw, I have to run it several times, and I don't want to use up your time here just watching the computer run. So now we're adding a buoy midline. And to do that, it's fairly simple. You copy the line definition, and I make I just copy paste it twice right below it. And I do need to change the class name. Okay, so I'm going to now call it wire B. Okay. In order for my mooring lines to all appear in the same picture, I'm going to go ahead and change the length of that first line to 500. And then I'm going to add the minus clump. And the minus sign for the force means that it's a buoyancy force. Okay, so element B is what I changed. I'm going to run it, and I'm just going to run it right there just enough so that I can show you the picture of the change in catenary shape. And here I'm going to have to zoom in again. And again, this is because Moses wants to put everything in one picture. So I'm going to now look at the system from the bow, and you can see now that there is a line, element B, that has two segments, and you can see where that buoy is located. So the buoy is there at the water level. Okay, and again, on the tabs, here is the green tab. It shows us what the weight of the clump is, and it shows that we can go up and down the segments, and it tells us the properties of the segments. So for the next thing we're going to change, it's going to be to change the properties of the second segment. So I'm going to go back to my command file, and this time I'm going to copy those two lines where I made my WB class, and I'm going to call it WC. But what I'm going to do is that second segment, I'm going to make it almost 5 times heavier. Okay, so now that the second segment is heavier between lines element C and element B, right, so we should get a deeper catenary. So the sag is going to be more pronounced. Okay, so I'm going to run it again. And we're going to see the view again where we can see both catenaries. And here we are zooming in, and you see that there are two catenaries. One of them has a deeper sag, and that is because the line is heavier. Okay, so those are some options for changing the line properties. Okay, and you can of course have more than 2 segments. Right, many times we have wire chain wire, so you would, instead of 2 lines, maybe you would have 3 lines. Maybe you're trying to avoid an obstacle, so maybe you might want a couple of buoys at different segments. I have seen up to 25 segments, so this list can get fairly long. Okay, so the next thing I want to show you as far as options go is simulating one-line damage in Moses. Okay, when we do, in our industry, when we do a global performance analysis, many times they want us to do a one-line damage. So here I'm going to show you how that is done with Moses. So I'm just going to quickly review what our setup is. Here's elements, the name of the elements again. And the reason I'm reviewing the name of the elements is because I want to again iterate that the environment is 90 degrees. It goes from the bottom of the page to the top of the page. And that means that lines F and G are expected to take the highest load. What I'm going to do here is I'm going to make a sensor on element G, and I'm going to tell it to deactivate the line at a certain tension. Okay. Here are the results from the tensions, and you see that this is a maximum of 610. I'm going to ask it to break the simulation at 350. Okay, so next I'm going to show you in the manual where the command is to create a sensor, and we're going to be using these 3 options. So describe sensor, we're going to be using minus signal, minus limits, and minus action. And what Moses is going to do is it's going to run that simulation, and when it sees that the tension in the G line is 350, it's going to deactivate it. And then it's going to continue with the simulation. and what we wanted to continue because many times in our global performance analysis, they want us to also simulate the transient, right, as the vessel repositions itself after breaking a line. So here is the analysis, and again, this is as quickly as it ran on my machine. So now we're going to review the results. So from one of the previous plots, the tension 350 occurred around event 115. So when we look at our movie, we're going to zoom in, and you're going to see, I'm going to pause it briefly after it breaks. Okay, and the reason I'm pausing this, so you can see that the line is deactivated. So here at time step 300, it's deactivated. When I move it back to 0, it's activated. I'm going to begin the simulation. And you see now the waves are going past it. And at the top is where the events are. So once it reaches 115, we will be able to see that that line is broken, and you can see the vessel is repositioning itself. And now we will finish the simulation. Okay, and of course we want to finish the simulation because we need to get all the statistics again, right? We want to get the maximum tensions now because we have less lines. Okay, we want to get, maybe we want to get the location of some points. Okay, maybe there's another vessel nearby and we want to avoid collision. Okay, so that's why we want to finish this simulation. So let's review the plots. So again, remember, it was elements F and G that had the highest load, and that I asked for the line to be deactivated at tension 350. So here is the port side, and you see that here's the starboard side, and you see that red line. It just, when it's deactivated, the tension goes to 0. So here it is with the intact case. So that's when the tension first reaches 350, and that you can see that that is where it is deactivated around event 110. Okay, and that was my presentation. And if there are any questions, I am here to answer them. I have these files available with me. If somebody has a question that they would like to see a certain one of these simulations again, I can certainly bring those up. I can here in my files if somebody would like to has some questions. Okay, here are some questions. Let's see. BCAT and HCAT do not consider drag for deep water, and for some projects it is important to include those. Is the rod element the right way to do that? Yes, that is the right way to do that. The rod element. Okay, so yes, I use the HCAT. I use the HCAT class, and I use the I use the PCAT class to do my simulation. But if I wanted to include added mass and drag along the length of the line, you would use the rod element. And there is in the test directory under connectors, one of the tests does use the rod element to show that there's a difference when you use the rod element to include added mass and drag and when you do not use the rod element. Okay.
We've just been having some technical issues with Dan that was going to be helping with these question and answers, so I've stepped up to the plate. I'm James Clarkson. I'm one of the support engineers that works with the Marine Offshore Project, the programs. This next question we have in for you, Georgina. What is the difference between the panel wave forces and the linearized wave frequency forces? Which one would you call load RAOs?
Okay. Okay. So the question is the panel wave forces, and then the linear RAOs. Is that
The linearized wave frequency forces.
wave frequency? Okay. The panel wave forces. Okay. So are you? Maybe I'm not understanding the question. The panel wave forces is the force on each panel. And the linearized wave frequency forces, that's the report that gives you what the force is as the entire body. So a panel wave force would be just a subset. The panel wave force is what's used to create the larger linearized wave frequency forces. And I think I'm misunderstanding that question. Because part of the other question was how, which one would be better, and I'm thinking one's a subset of the other.
Okay, maybe we'll see if we get any further question onto that one. A simpler question for you. Where does Moses mooring analysis fall under? Coupled or decoupled analysis?
Oh, it's fully coupled. So and including the rod element, if you wanted to use the rod element for risers. So the we do compute the RAOs, but in the time domain analysis, okay, yes, so yes, my whole answer here is about time domain. In the time domain analysis, the change in catenary shape will change the response of the vessel. The change in response of the vessel in turn changes the catenary shape. And the same is with any rod elements that you might be using. If you are using rod elements for mooring or risers, again, it is a truly coupled analysis.
Great. And I've got a question if you can do another demonstration for us. Oh, I'm not sure if the screen's still available, Georgina. What about the catenary profile plot? Are you able to do a catenary profile plot for us?
Okay. Well, sure, let's try that. So okay, so we want to know just the X and Z location. So I'm going to put, okay, so here my tension, I'm going to change that. Put an end of file. Okay, so for example, okay, so here is the system I am working on. Okay, and they want to know the profile part. I am assuming they want a Z and X location. Okay, first of all, to get that, if you do status DG connect, right? Here, for example, here is where the raw data is. So distance here is measured from the anchor. So here distance is 0, and you see Z is 500. Okay, so you could either plot the X versus Z, or maybe they want the distance versus Z. Okay, that. Okay. Okay, so maybe this is one of the times where I would export this table to Excel or SQL and then plot it that way. Okay, next question, James.
Cool. So the next question is how does Moses calculate the second order term near field, midfield, and far field?
Okay, good question, because Moses 10.01 just came out, and in Moses 10.01 we added the far field wave drift method. I see that we're running out of time, and this actually discussing the the far field and the near field, it's that can actually take a good deal of time because it's very mathematically and theory oriented. If the person that asked that could either send me an email or submit a service request, I will be sure to answer that one in more detail. But yes, we do now do far field and near field methods.
I've got to say we have a lot of questions that have come in from this presentation, which is always a fantastic sign that people are either having some great questions out there, some great experiences out there that they need questions for, or we've raised some thoughts. I think this may be one of our final questions we get a chance to get through. Is there any way we can see the stiffness of the whole mooring system? For example, Ariane 7 shows the stiffness in longitudinal and transverse directions.
Yes. As part of the files, you see here, did I leave part of it? I did not. Okay, so here we would go into connector design menu. Oh, because I'm in the wrong. Okay. So here in the connector design menu, there's this command move. Okay, so I'm going to move maybe the 90-degree direction, maybe 15 steps. Okay, and then here's the restoring force versus excursion. And so we have the X restoring force or the Y restoring force. Okay, you can also do it. Okay, so I did it for 90 degrees. So obviously the X excursion is going to be 0. Okay, but we can certainly plot the Y excursion versus the Y restoring force, for example. And there would be, so this would be the stiffness of the mooring system, which I'm glad this question came up because, right, there, when you're doing these types of analysis, you have to look at the line individually and get a restoring force for the change in individual catenary shape, and then you would need also this type of plot where it's the stiffness of all of the lines together as excursion. So great question. Thank you for bringing it up. Thank you very much, and I do appreciate your time.